Awesome. So I'm Mary Kate, and our group was working on trolling for pace. Let me see if I can. So we focused on the Northeast Fisheries Science Center's bottom trawl survey, and we particularly just looked for species that were the most abundant during the survey legs that overlapped with pace. And so we settled on silver hake, mostly because it just had good spatial coverage across the legs. And just for some background on the species, they're a groundfish fishery. There's some papers linking their distribution to Gulf Stream. And there's some papers showing that there's condition abundance and recruitment linked to zooplankton, SST, and plankton blooms. So they seemed like a good species where we could have some fun playing around with the data. For those who aren't familiar, the Northeast Fisheries Science Center Bottom Trawl Survey is in the Northwest Atlantic. It runs twice a year, generally in the fall and then in the spring. And overlapping with PACE, we have fall and spring 2024 and just spring 2025. Fall 2025 is complete, but the data is not audited and publicly available yet.
So for our data sets, we used a mix of the Fisheries Institute data and some remotely sensed data. So for the remotely sensed data, we used FSLE, which is finite sized Lyapunov exponent, which is something I'd really never heard of before, but it's really intriguing. It's a Lagrangian diagnostic that's used to detect ocean fronts, mixing, and transport features. So Leandro calls it the invisible fence in the ocean. And so high FSLE values indicate convergence points in water masses, fronts, regions of intense mixing, which often correspond to biological hotspots. We also grabbed some wind stress curl data from Copernicus. And then for PACE data, we grabbed the RRSs and AVW. For our in-situ data, we used the silver hake catch abundance numbers. And then on the survey, they had taken some in-situ bottom temperature, bottom salinity, and bottom depth measurements that we used. So our main objective was we were wondering if we can predict silver hake abundance using optical data. And beyond that, a lot of us in the group had some interest in machine learning. So we wanted to compare performance from a couple of different models.
Yeah, this is the workflow of our work. So we have data from observation and also data from space, from PACE and from satellite, Aviso and Copernicus. And we applied the mashup of that one, and we got a final data that we applied two different model, random forest model, and boost regression retrace model, all of them in order to get a prediction. After that, we do the comparison between the different observation and the predicted values, and enter comparison between the model and then the visualization. Next. So yeah, continue.
Oh, sorry. So for our matchups, we matched pace data following the HackWeek tutorials, and this is something I worked on. I do not have a lot of experience with Python or pace at all. So the tutorials are really helpful in like walking through how we did that. So that was super helpful. And then Leandro worked on pairing some of the other data with the catch data.
So then there's the problem with overfit models. In a typical machine learning setting, we split the data randomly, but ocean data is sequentially connected. So for example, what happens at 9 a.m. is going to be almost identical to what happens at 9:01 a.m. And so if you have data from 9 o'clock and you put that in the training data, and then you have data from 901 in the test data, the model isn't really learning the physics of the environment. It's essentially cheating because it already knows what that data looks like, because the 9 a.m. data looks almost exactly like the 901 data. And so to fix this, we can use natural gaps like night cycles or cloud cover to group the data into temporal islands. And so if we temporally split the data, we can ensure that a data point going into the training set and has its immediate neighbors go with it. So the temporal island is never split. And by creating these buffers, we can reset the autocorrelation and force the model to actually generalize.
So for the study, we have used two models, the random forest and the boosted regression trees. So from the feature important analysis, the important variables for this prediction were nearly the same. And the major conclusion is that these physical variable like the bottom salinity, bottom temperature, and the spatiotemporal variable like latitude, longitude, the day of year, and these depth are very dominant factors compared to the spectral reflectance. And next slide. So from this silver hake prediction using machine learning, and we have mapped their prediction. So these figures are showing the prediction from random forest, boosted regression tree, and the original BTS catch data. So from this original BTS catch data, the silver hake catch number were very high, especially in the southern Scotian shelf waters. And when we saw this from the figure comparison, the model have a moderately captured the patterns of this silver hake abundance. And from the residual analysis also, we can found that this random forest and boosted regression tree performance were it's somewhat similar. But when we done the statistical analysis, the coefficient of determination value R square were higher, and the root mean square error were lower for this boosted regression tree. And the Wilcoxon p-value that indicate that these models are statistically significant. This model shows statistically significant difference, even though the mean difference is very low. Next slide.
So some of our limitations, obviously, who doesn't always want more in situ data? But like Mary Kate mentioned, this is a growing data set. So bottom trawl goes out twice a year. So maybe in the next year or two, we could revisit this and see how model performance improves. We also, if we had time, we would have loved to explore adding additional variables. We were really intrigued by using Moana. We would have liked to incorporate some commercial fishing data just to buffer up our in-situ data set a little bit, and other additional surveys. We also would have liked to test some other species and some other models. I know a few of us were really hoping to be able to have time to do a neural network for this. And then finally, we just linked our project GitHub and our individual GitHubs there, so you can all see our work. And then we just wanted to give a big thank you to Ryan, Eli, all the mentors and all the helpers and organizers for organizing such a wonderful HackWeek. We all learned so much and are so appreciative of your time and effort in organizing it.